So hello students. So in this video lecture we shall be seeing today what is Griffiths energy criteria. So here, to know this Griffiths energy criteria, we come across the term called as the fracture strength or the fracture strength of ideal materials, or even you can say strength of ideal materials. So we shall see first what is this strength of ideal materials. So we shall see this derivation. We shall obtain the expression for sigma f in this derivation, and using that equation we shall be seeing what is Griffiths energy criteria. So here you can take down this diagram. So here in this diagram, it is the two atoms of a material which are joined together, and these material or these atoms have a distance from the nucleus to nucleus as the x naught, and to break apart this atom we need to apply the tensile load, because compression load will not help in breaking these atoms. So when two atoms are situated, when they are close to each other, they are in contact, we need to apply the tensile load. So at tensile load there will be breakage of this bond, and that breakage of bond is nothing but the fracture of the material taking place at microscopic level. So here we shall see now what is the stress required to break this particular bond. So here we make some assumptions. So the first assumption what we make here is the material is said to cleave. Cleave means it is said to break, and when it breaks under the normal stress, the separation of atoms is along the direction of the applied stress. So here the separation of the atom is along the direction of the applied stress sigma. So this is the first assumption. The second assumption what we make here is the atoms separate simultaneously. Since their separation reaches a critical value, it is not that only first two atoms of that material separate or first six separate or anything. All the atoms which are situated in that particular material will separate at the same time. That is, say for example, we have a material here comprising of numerous atoms over here which are joined together. When you apply load, these atoms will separate simultaneously. It is not that there will be first separation, then second separation, then this way. It is not happening in this order, but it separates simultaneously. So we start with these two assumptions, and The last thing what we assume here is the stress concentration at the tip is neglected. That is, when the atoms cleave over here or separate, there will be a small notch like formed in the material, and the stress tends to concentrate at this notch, so that stress concentration is neglected. So these are the three important assumptions. So here let us discuss about this drawing which we have done. So in this graph, the tensile force is required to increase the separation distance, which must exceed the cohesive force to split the bond separately. So what it means that there are two atoms which are joined together using the cohesive force, that is, there is some attraction force among themselves due to which these atoms are held together in any material. So if you take this chalk is made up of calcium, the main element, and some other sub-elements. Together they form this compound from which this chalk is made. Now, for this chalk to remain in this condition, all the molecules and all the atoms should be held together firmly and they should not separate. They will separate only when, in the case, we apply some load. Now, in this case, for this chalk, when I apply the bending, there will be stresses developed and that will cause the atom to break. Now here, one thing to note, whatever the amount of force I have applied here to break this chalk is more than whatever the cohesive force is there within these atoms of this chalk that are held together. So when this force exceeds, there will be breakage of that material. So now, this is the first thing. So in this case, we shall denote few parameters. So what are those parameters? First, we denote EB as the bond energy. So what is this bond energy? The total amount of energy that is present when the bonding is taking place. Then we assume when we take P as the applied load, applied force or applied load, and we take the x0 as the equilibrium spacing. So what is this equilibrium spacing? Equilibrium spacing is nothing but the same distance between the two nuclei of the bonded atoms, like in this case. So this is equilibrium spacing. Now we have taken these three terms. So using these three terms, we shall now derive the expression for the stress that is required to break this bond. So here, first thing we take here for the expression for bond energy. So here bond energy EB is given as, now if you see here, it is from x0 to infinity. So we integrate from x0 to infinity, okay, the applied load along the x. That is, we have applied load P. So this P is integrated along dx from the limit x0 to infinity. So whatever may be that length, so total that length will give the bond energy. Is that clear? So now from this expression, it is possible to estimate cohesive strength by force displacement relationship as 1/2 of the period of sine wave. So what it is, the force displacement relationship is given by, so I'll write this EB from top here once again. So this EB is equal to integral x0 to infinity P dx. So force displacement relation is given by the applied load P will be equal to the cohesive force into sine of pi into x by lambda. Okay. So x is the total distance and this lambda is this distance from x0 to this point. We take that as the wavelength or the lambda. Okay. So it is 1/2 of the period of sine wave. So this is for the force, that is force displacement relationship. If I divide this by area on both numerator and denominator, what I can get, P by A will be equal to sigma, PC by A will be equal to sigma C, and this will be remaining as it is, sine of pi x by lambda. Do you agree with this? From load displacement relationship, I calculated I found the stress displacement relationship. So this stress displacement relationship is equation number 1. Now here PC and sigma c, as I told, are the cohesive force and the cohesive stress respectively at a distance x. So when there is small displacement x, we can write this as sigma is equal to sigma c into pi x by lambda. The sine term gets eliminated because sine of theta will be equal to theta when theta is very small. So in that case, this term is nothing but the theta term. So sine of theta when theta is small will be theta. So I just write this theta term as it is. So we get sigma is equal to sigma c into pi x by lambda. So for both these equations, I multiply by x naught. That is, I'll write this as sigma into x naught is equal to sigma c pi x into x naught divided by lambda. Now this x term, I'll take it to the denominator over here. So I'll just continue this on this side of the board. So I can write that as sigma x naught upon x will be equal to pi x naught upon lambda. Is that clear? Into sigma c. Is that clear? So this I take it as equation number 2. So let us focus only on the LHS of this equation 2. So LHS, I'll take it as sigma x naught upon x. So for this, I can write this as sigma will be nothing but p by a into x naught by x. Do you agree with this? Only I have taken this LHS, and this LHS I have written here, and the sigma I have taken as p by a, and x naught by x I have kept as it is. So p by a, and we have x naught by x. So I'll just rearrange these terms. So this I can write as p by x into x naught by a. Now if you see, what is load divided by length? That is p by the distance x. This becomes k, and that we call it as stiffness of this material. Load by length is nothing but it is the stiffness of the material. So we get the LHS as k into x naught by a. So here the term k into x naught by a is the measure of the Young's modulus for this material. So now equation 2, I can write this as, since this becomes Young's modulus, this will be E. So here equation 2 can be written as, I'll just take it again this side. So equation 2, I'll write this in the LHS as E, because this term is nothing but it is the Young's modulus, that is stiffness into x naught by a will be Young's modulus. So E will be equal to pi by x naught upon lambda into sigma c. So here I'll do some modification to this. Sigma c will be equal to E into lambda upon pi into x naught. So this I take as equation number 2. Now here, if lambda is assumed to be approximately equal to the equilibrium spacing, so if lambda is approximately equal to equilibrium spacing, that is lambda is approximately equal to x naught, we can write this sigma c will be equal to E by pi. Do you agree with this? Because lambda and x naught will cancel if they are approximately equal to each other. So now this is the expression for the cohesive stress, that is sigma c. But ultimately we want the expression for fracture stress, which will be greater than this cohesive stress. So now here one thing we need to note: when a material fractures, there will be new surfaces created. How that new surfaces will be created? Say for example, you have a plate which is present this way. There is, you are applying a load and there is a small crack, and this crack opens up in this form. So I am just drawing some exaggerated image. So here you will have one surface which is created, which is the new surface created here. Similarly, you will have another new surface which is created on the bottom side. That is, when this is the material, when this opens up or fractures, one surface is the bottom surface and the other surface is the top surface. So two surfaces are created. Now here, to create that two surface, we need some energy, and that energy is called as the surface energy. So here, the surface energy or the energy required to create new surfaces per unit area is equal to half of the fracture energy, because two surfaces are created when the material fractures. So the equation for creation of one surface is given by nu s or gamma s, whatever you take. So that is the energy required to create one surface. So we write this as half into integral 0 to lambda, because surface has to be created for the length lambda. So 0 to lambda sigma c, that is the cohesive stress, into sine of pi x by lambda dx. Right? So it is integration of the total stress which is developed from 0 to lambda and half of that. So again, I'll read that definition. So to create surface energy per unit area is equal to half of the fracture energy. So fracture energy is nothing but integration of this fracture stress will give the fracture energy, that is sigma. So half of the fracture energy will give the equation to, or the energy to create one new surface. So now I will simplify this integral. So I can write this half, sigma c being constant will come out, and integral of sine pi x by lambda can be written as minus cos of pi x by lambda upon pi by lambda 0 to lambda. Do you agree with this? So this I will simplify. So simplification, minus sigma c by 2, and again lambda, pi by lambda is in denominator, so when I take it out it becomes pi lambda by pi, into, first I will write cos of pi into, when you substitute for x lambda, lambda by lambda is 1, so what we get is minus, or minus I have taken outside, so I will just write positive here. So cos of pi, okay, minus cos of 0. So cos of pi is 1, and here, one second, yeah, cos of pi is minus 1, so this becomes sigma c by 2 lambda by pi. So cos of pi is minus 1 and cos of 0 is plus 1. So here this becomes minus 2, that 2 and this 2 gets cancelled, and ultimately what we get this as sigma c into lambda by pi. So we get this equation as nu s is equal to sigma c into lambda by pi. So this, we have already taken this equation 3. So which is that equation 3? Sorry, here we have this as equation 3. So when I substitute this equation 3, that is sigma c over there, that is in place of sigma c I substitute that equation 3 in the equation. So I get that equation as nu s will be equal to sigma c can be written as E lambda by pi into x naught into lambda by pi. So here this can be written as E into lambda square by pi square x naught, that is nu s. Do you agree with this? So also from this equation number 3 we can calculate lambda by pi will be equal to what? From this equation 3 what will be lambda by pi will be equal to? Lambda by pi will be equal to sigma c into x naught upon E. Do you agree with that? Okay. Sigma c x naught upon E is lambda by pi. So that lambda by pi I'll also substitute over here. So I can write this as E into sigma c square so I'll substitute here for sigma c square into x naught square upon E square for sigma c. Okay. So into 1 by x naught. So did you get this? So what I did here, E I kept as it is, lambda square by pi square, I substituted sigma c square x naught square by E square into this x naught remains as it is, so 1 by x naught. So this is x naught. So in this now, one term of x naught gets cancelled, then E gets cancelled. So what ultimately remains over here is sigma c square into x naught by E. Do you agree this? So we get the surface energy, that is nu s, to create one surface as sigma c square into x naught by E. So I'll just erase this and write everything once again here, that equation. So here the surface energy nu s to create will be equal to sigma c square into x naught by E. So I'll write this as sigma c square will be equal to nu s into E by x naught. So sigma c will be equal to root of nu s into E upon x naught. So we have the equation for the cohesive strength, that is sigma c will be equal to root of nu s into E by x naught. So this equation we call it as the ideal strength or the theoretical strength. And with this cohesive stress we shall now see the Griffiths energy criteria, or it is also called as Griffiths energy balance. So there is one diagram, I'll just draw that diagram. So here, before we start with the Griffiths energy balance, we need to first see what is the first law of thermodynamics, because this derivation is based on that first law of thermodynamics. So are you all aware of what is first law of thermodynamics? Yes. According to the first law of thermodynamics, when a system goes from non-equilibrium state to equilibrium state, there is a net decrease in the energy or it remains constant. That is, when a system goes from non-equilibrium state to equilibrium state. That is, say for example, you have a system which is nothing but a vessel of hot water. You keep it in the room temperature. So what happens? That hot water is in non-equilibrium state, and when it comes to room temperature, the temperature of water and the temperature of the room almost they become equal, though it will take some time, so it becomes equal. So when it becomes equal, that is, that vessel comes from non-equilibrium condition to equilibrium condition. So in that state, there is a net decrease in the energy, or it remains constant, but it will not increase. Is that clear? Say for example, also in this case, this is one example where the energy will decrease. In the second example, you have a vessel of hot water whose temperature is say 85 degrees. You immediately take it and keep it in a furnace whose temperature is also 85 degrees. So what happens? From non-equilibrium state, that is when its temperature was 85 degrees inside the vessel and outside was the room temperature, it was in non-equilibrium state. But you took it immediately and kept it in a furnace whose internal temperature was 85 degrees. Then what happened? From non-equilibrium state, it came to equilibrium state. But if you see, the amount of energy it had when it was in non-equilibrium and the amount of energy it has now in the equilibrium will be same, but it will not increase, or it will be same. And if the non-equilibrium to equilibrium is the other way, that is from hot to room temperature, when you get it, it will decrease. That is what he says, that the energy or the net energy is decreasing or it remains constant. Is that clear? So with this in the mind, we can apply the same rule to this Griffiths energy balance. So in the figure, you have a solid body with an internal crack. So a crack can form or grow if such a process causes the total energy to decrease or remain constant. Thus, the critical condition for the fracture is defined as the point where the crack growth occurs with no net change in the total energy. So we consider this plate subjected to constant stress sigma. So you can see here, this is the constant stress sigma, which contains a crack of length 2a. In order for this crack to increase, sufficient potential energy must be available. If there is no potential energy, then there won't be any crack growth. Okay. So potential energy must be available in the plate to overcome the surface energy of the material. So that energy can be given as the energy E will be equal to U plus Ws. So say this as equation number 1, where E is the total energy, U we have is the potential energy, and Ws we have is the work required to create new surfaces. Is that clear? Or one surface, you can say, work required to create one new surface. So now, according to Griffiths energy balance, for an incremental increase in the crack area, that is dA, we take it as incremental increase in the crack area, that is dA. If capital A is the area of the crack, so dA will be incremental increase in crack area under equilibrium conditions. Then equation 1 can be written as, so this equation 1 we can write it as dE by dA will be equal to du by dA plus dWs by dA. Now what it means? For a small increase in area, there will be small increase in the energy, that will be small increase in the potential energy, and that will be small increase in the energy required to create, or the work done to create the new surface. And since it will be in equilibrium condition, this will be 0. Okay. So this I can write now as du by dA will be equal to minus dWs by dA. So this, you take it as equation number 2. So where we can write A as 2A into B from the figure. So 2A into B will give the area of the crack. So there was another scientist named Inglis, not the language English, it is Inglis, I-N-G-L-I-S. So he showed that the potential energy in the system will be equal to the potential energy of the uncracked plate minus pi sigma square A square B by E. That is, he gave the equation. So Inglis gave the equation U will be equal to U naught minus pi sigma square A square B upon E. So this you take as equation number 3, and Griffith used this stress analysis of Inglis to show that the potential energy U is the potential energy of uncracked plate minus pi sigma square A square B by E. So what happens to this work done? Now let us see the expression for work done to create one new surface. That is, Ws will be equal to 2 times the area into the energy required to create new surface. So this can be written as 2 into 2AB into nu s. So that is 4AB nu s. So this will be equation number 4. Clear? So that is the work done to create one surface. So now we shall differentiate equation number 3 with respect to small a, that is half the length of crack. So let me write that differentiation over here. So differentiate equation 3 with respect to small a. So what we get when we differentiate this? So du by dA, u naught being the constant will be 0, and this can be written as pi sigma square 2ab. Pi sigma square b and e are constant, so pi sigma square b by e, and a square can be written as 2a, that is derivative of a square is 2a. So this I'll simplify. So du by dA, this 2b I'll take it to the denominator, will be equal to minus pi sigma square a upon e. Now what is this? 2ab, 2 into a into b, that is the area. So this I'll write it as du by d into capital A. This will be equal to minus sigma square a by e. So let us take this as equation number 5. Clear? So you just note this down, because I'll be erasing, because now I have to differentiate equation 4 also with respect to small a. So here at one point I'll just write this so we may require this. So I'll write this as du by dA will be equal to minus pi sigma square a upon E. That is equation number 5. Okay. Now I shall differentiate equation number 4 with respect to small a. So what I get this as dWs upon dA will be equal to, here 4b and nu s will remain constant. So this will be 4b nu s, and what about the derivative of a? That will be 1 into 1. So this I can simplify by taking this 2b from this equation over here. So dWs by dA into 2b will be equal to 2 into nu s. Do you agree with this? From 4b, 2b I have taken here, so what remains is 2 and this nu s remains as it is. Now what is this a to b? It is capital A. So dWs upon d into capital A will be equal to 2 nu s. Say this as equation number 6. So I'll write this equation 6 over here for our reference. That is dWs upon d capital A will be equal to 2 nu s. So now we had equation number 2 as du by dA was equal to minus dWs by dA. So in this equation number 2, so this was our equation number 2, so you might have written it, so you can just refer that. So in this equation 2, we'll substitute equation 5 and 6, so this will be minus pi sigma square A upon E, this equal to minus 2 nu s. Do you agree? So this minus and this minus gets cancelled. So what you get is pi sigma square A upon E will be equal to 2 nu s. So we solve this for sigma square. Sigma square will be equal to 2 nu s into E upon pi A. Therefore, sigma can be written as 2 nu s, that is root of 2 nu s into E upon pi A. And if this stress has to be fracture stress, we write sigma f will be equal to root of 2 nu s into E upon pi A. And this is the equation that we require for determining the fracture strength. Now suppose if there is a plane strain condition, this will be for plane stress condition. For plane strain condition, we have 2 nu s into E upon pi A into 1 minus gamma, or this gamma is the strain, that is the Poisson's ratio, sorry not strain, this is the Poisson's ratio, or you can say mu or gamma, whatever it is. So 1 minus gamma square will come in the denominator for Poisson's ratio. So here this equation is required to determine the fracture strength. So in the next class, we shall be seeing the definition of types of fracture and failure, and then we'll also see the introduction to strain energy release rate, and also we'll be solving few problems on this Griffiths energy approach. So with this, that is with tomorrow's lecture, we'll complete the first unit in fracture mechanics. and then we shall start with the second unit after the tomorrow's lecture. So that's all for today in this lecture. So please watch this video, make your notes according to the explanation in the video. Please prepare for these through this video lecture for your exams. So thank you very much.